This is Lesson 5 of Unit 7, Euler's Method. So in our study of differential equations, we've been given a very restrictive set of separable equations. However, what happens if we can't separate it and we still need to solve it? So what we're going to do is we are going to use a numeric approach. We've done graphical approaches in the first part when we were especially looking at like linear motion. But Euler, who was a Swiss mathematician, came up with a numeric approach for approximating a differential equation. So the idea behind that is this. What you want to do is, if you see underneath here, we have the actual curve of a function here. And then above it, what that is our approximations. So the whole idea is you're starting at point 0, some point that you know you're given, an initial value. Then what you're going to do is you're going to draw a tangent line from on that point, and it should hit point 1. And then what you're going to do from there is once you have that value, you're going to draw its tangent line. That's like really off, so let me try that again. Its tangent line. Sorry, I was on my eraser. So I have my first tangent line here through point 1. And then I'm going to draw the tangent line here. And if you see, it should cut through point 3 and continues. Then you do this. And so as you see, we are making our case for how to draw this approximation curve. Okay? So if you see them together, what you can do is on the slope field, you can see how they're related to each other. Okay? So the idea is that if we're talking about now, if you zoom in on a very small area, we can display local linearity, and so that you want to be as close as possible. We're really zooming in. We want a really small delta x so that the value of the slope at that point will be almost exactly the same as the value of the function. So the idea is to make those small calculations, move that little differential amount, and you're going to approximate the actual curve. So usually what you do is you make a chart. And the way the chart works is this. You're going to calculate your change in y as you go. So you really, what you're doing is you're going to take your next y value, or your change in y, is going to equal to the initial y value plus your slope times your change in x. Okay? So that's the idea. So you're adding those little differential changes. So let's go through one. So for this example, we're given that dy dx is y, and we're given the initial condition that when x is 0, y is 1, and we're going to make steps of 0.1. So how is this going to look in this table? It looks like this. So we know we started with an x of 0 and a y of 1, and that's going to be a slope of 1. And so our tangent line is going to look like y equals x plus 1, because you're going to have x minus 0 plus 1. So then when we add our delta x to our initial x value, we're at 0.1. So then our new y is going to be, we're going to substitute it into the tangent line equation. Okay, so we're going to get 0.1 plus 1, so we get 1.1. And now we're going to repeat that process. So now our new x is 0.1. Our new y is 1.1. And so we're going to use our equation here, dy over dx, which is equal to y, to get our new slope, so that's 1.1. And so our new equation for our tangent line will look like this. Our new slope times x minus x1, and then our plus y1. Okay, and then you just keep repeating the process. So then our new x is going to be 0.2, and then you substitute that into your tangent line equation to get your new y. And when you do that, you get 1.21. And you just keep repeating that process. So I'm going to display the whole table here for you. Okay, so here's the whole table filled in. And I just want to point out that it's unusual that the y value and the slope are the same. The reason for that is, of course, the fact that our differential equation is just equal to y. So the slope and the y value will be the same, but that's just a special case. So you should go through and do that table yourself and see if you get these values. All right, next. How do you go about doing this? So here is the method for solving a differential equation. So you solve the differential equation for dy. So you want all the x's, the y's, everything on the other side of the equation. Then you substitute in those to calculate your dy. So you're looking for your slope, really. Then you approximate your new value of y by adding that value you found in step 2. You add to it the previous y. So what you do here for step 3 is you take step 2 and you do step 2 plus your y, your previous y. And then you just keep repeating that process over and over until you get to the y that you want. Example 1, show that Euler's method for dy dx equal to 0.5 x plus y starting at 0.2, 1.11 and using 2 steps with a delta x of 0.05 gives y approximately equal to 1.1775 when x is 0.3. So what we're trying to do is we're trying to find the approximation of y of 0.3 for this differential equation. So I'm going to blow my table up here a little bit, whoops, so that I have some more room because the numbers get a little long in the decimals, so I'm going to make this a little bigger here. Okay, so I have some more room to write. All right, so our dy here is going to be, what we're going to do is we're going to take our y prime times our delta x. And we're going to use our formula here, our differential equation. Dy is going to be 0.5 times x plus y. We're going to substitute that in there and then multiply it times the delta x. And then what we do is we add this to the y to get the new y. Okay, so doing it the first time, we're going to have 0.5 from the formula, and then our x is 0.2 plus 1.11, and we're going to multiply that times 0.05. And then we're going to add that to 1.1, and we get a new y value of 1.14275. So now our new x is going to be found by taking our previous x and adding our step. So each of these are going to get added 0.05. I can't put the plus there, it's too close to the edge. So this is 0.025. My new y is now the one I just found in the last line, 1.14275. And now I'm going to use those two values and substitute them into my equation here. So I have 0.5 times, and now I'm taking 0.25 plus 1.14275, and I'm going to multiply all that times 0.05. And when I do that, I get a new y value of 1.17756. So I just have to do it one more time, because when I add my next x, I am at the x value I'm approximating, 0.3, and I have my answer, because at 0.3, x is 1.17756, which is what we were hoping it would be. So we did verify it. Okay. So you guys try the next one. It's the same idea, and the table just looks a little different, The only reason for that is you might see the table looking different ways. So I'm going to pause the video. You guys should fill this out, and then you can check your answers. Make sure you can do all this number crunching, because you may have to do it on the test. Okay, so here's example 2's table. I did put the calculation for the first delta y in the first row here. And I did the same calculations using this differential equation to find all of those delta y's. Okay, moving on. How accurate is Euler's method? So the error in using Euler's method is just like you do for any other error analysis. You're going to take the exact value minus the approximate value. So if a number of steps used is n, the approximate error is proportional to 1 over n. So what we're doing here is we're comparing the tables below. Each represent a specific solution to a differential equation. The one we did on the front page, dy dx equals x, where y of 0 is 1 and our delta x is 0.1. And Euler's method is the approximation. So the first table is the approximation, and the second table is the exact solutions. And it turns out that this particular solution is e to the x. So looking at that, we're going to answer these questions. The first of which says, the graph at right illustrates the particular solution as it compares to the Euler approximation. And what you'll notice is that it is an underestimation everywhere. So why do the approximate y values underestimate the actual curve? Now these are the kind of questions that you will get. You want to think about it in terms of how we analyze graphs. And what you want to notice is that this graph is concave up. So what does that mean about where your tangent lines will be? The tangent lines will always be underneath. So that's why. So that's the kind of answer you're going to write. So you can write the curve of y is concave up. So the tangent lines are drawn below the curve. Therefore, there is an underestimate. Okay, so something along those lines if you're answering a question like this. All right, now part B says complete the table at right, comparing the difference between the exact minus the approximate value. Why are the approximations getting better or worse, and why? So let me just fill those in really quick. So you start at the first point, so that's usually spot on. There's no difference there. And then the next change is 517, and then the next one is going to be 0.0114, and then the next one is 0.0188, and then we have a difference of 0.0277, and the last one is 0.03819. So what you see is these numbers are growing as they get down. As you go down, they're growing. So what we say that the approximation is getting worse. And the reason for that is that y equals e to the x is exponential. And the curve gets steep or steeper very quickly. So the slopes at larger x's are going to be much steeper than they are for smaller x's, so that difference between the two curves is going to grow. Okay, what can be changed to make Euler's solution curve more accurate? If you think we're jumping by 0.1 every time, So what we can do is make a smaller jump so we're closer to our next point. We want to remember local linearity requires a very tiny neighborhood. So you can make or can choose a smaller delta x. That's the best way to do it. Okay, we're going to practice these in class. That's the end of the actual use of Euler's method. So it's just a matter of doing some number crunching and understanding how to get the numbers in the table and where they come from.